Well, hello everyone. My name is Joe Watson. I am a fourth year PhD student at the University of British Columbia's Statistics Department. And today I'm fortunate enough to be able to present a really cool project that I was involved with my fantastic supervisor, Marie OJ Mete, and the excellent team at SMIU Consulting, that is in particular Ruth Joy and Dom Tollett. And this work was actually for the Canadian Department of Fisheries and Oceans. And so Sheila Thornton was the wonderful research scientist who we worked with on this. So today I'm going to be talking about how we estimated the space use of the southern resident killer whales. So the southern resident killer whales are an ecotype of killer whale. They are listed as endangered under both the Canadian Species at Risk Act and the US Endangered Species Act. There are 3 pods of them, distinct pods, J, K, and L. Unfortunately, every time I give this talk, the numbers seem to change, well, drop. So today there's 72 of them left. And so essentially, the Canadian government recently announced the Whales Initiative. And so this is a 167 million Canadian dollar initiative to help protect the killer whale, or the southern resident killer whale in particular. And so they have 5 deliverables in this initiative, and all 5 deliverables really require accurate, high-resolution spatiotemporal knowledge. So basically knowledge where they are month to month during Chinook season, that is May to October. So the study region we consider is this green box you see here. And we have a ton of data. We actually have over a terabyte of data that has been collected on the southern residents from way, way, way back. But the 2 that we're going to consider, the first is we're going to consider data from, I would argue, the ultimate citizen scientist. This is a member of the public who was funded by the Canadian DFO, who put a GPS tracker on his vessel. He's considered an expert, so he was able to cite the southern resident killer whales, identify them on a pod level, and you can see those by the red markers. So the red markers are where he cited the southern residents, and the black markers are his GPS devices. Logged locations. The second data set we're going to consider is this massive citizen science database kept by 2 agencies. So the first agency is a Canadian-based BC Cetacean Sightings Network. The second is the US-based OrcaMaster dataset. Now, these contain sightings from a vast range of observer types. We have members of the public, we have ferry operators, we have lighthouse operators, we have whale watch operators, you name it. So essentially the task then became, how can we combine this presence-only data with the presence-absence sort of high-quality data that we saw previously? So to be able to combine these vastly different data sets together, we require some simplifying assumptions. So the first 2 that we make, the first is that we assume that the autocorrelation in each of the pod's locations disappears overnight. So basically an overnight window is enough time to allow them to sufficiently mix. And we could test this with autocorrelation plots. So we did this. The second simplifying assumption we make is that observers do not know the locations of pods prior to the first encounter. So basically the observers can move independently or are moving independently of the southern resident killer whales, and they don't know precisely, so they haven't been tipped off about their locations. So using these 2 assumptions, we keep only the initial daily encounters with each pod. So we turn to point processes as the toolbox to use. And point processes essentially help us to describe the distribution of a point pattern and help us to link it to things like environmental covariates. So if we wanted, we could define these 2 regions, these 2 blue disks, and we could try and model the number of points that fall within these disks and link these to covariates. We are in the space-time setting, so we define a spatiotemporal intensity, lambda, and this is going to be quantified at position S time t as the expected number of points per unit space-time volume around S and t. So the inhomogeneous Poisson point process is the most basic, useful process that we can use for this example. So this allows us to describe the space use using measured covariates, sea surface temperature, chlorophyll A, other measures of productivity. And we can allow lambda to vary across space and time as a fixed effect, and we can link it to covariates in a log linear way. And this allows us, basically under the point process assumption, for any region capital S, time interval capital T, we can model the number of points that fall within S and T as a Poisson distribution. And the mean of this Poisson distribution is going to be the double integral of the intensity surface across T and across S. Now, the issue with the inhomogeneous Poisson point process is that it assumes that the variance of the count equals the mean of the count for any region and time interval. Furthermore, for any disjoint regions, A and B, it assumes that these counts are independent given lambda. In practice, in ecological practice, there will be a whole host of unmeasured covariates, biological processes that will truly drive the space use of these animals. And so we want to be able to capture this additional clustering that is not explained by the inhomogeneous point process. Additionally, we want to capture additional clustering due to these unmeasured covariates. So, as with all good statistical regression-based methods, we can let our intensity vary across space and time as a random effect. So this allows us to do this, we simply include a random effect inside our linear predictor. And what we do is we put Gaussian random fields on this. We specify spatial and spatial-temporal covariance structures to help capture these additional spatial and spatial-temporal correlations. And this is called a Cox process. But our use of a Gaussian process here for Z means we're in the log-Gaussian Cox process framework, as Rick was. So the issue is, these have had great success for static species, but for very highly mobile species, they typically require very stringent assumptions on either no movement of individuals across discrete sampling units, or they require assumptions of no movement at all. Now, we have continuous detections in continuous time, in continuous space. We don't have discretely defined sampling units. So we need to generalize this to the case of estimating the utilization distribution of a highly mobile species. To do this, we redefine lambda as the expected encounter rate. To do this, this requires knowledge on the observer effort. Namely, we need an observer effort intensity that captures the instantaneous amount of effort at any point in space and time. And then we can just decompose our observed intensity, space-time intensity, into a product of observer effort with expected encounter rate. We can extend this further if we believe there are issues with detectability, and we can model a detection probability surface that also we can link to a set of covariates and whatnot. So we can decompose it into this triple function. So the issue with this previous equation, I'll quickly skip back to it, is that this requires us to be able to estimate or to have knowledge of all our observers at any instantaneous point in time and space. In reality, we're not going to be able to estimate from the presence only citizen science data where the observers were at any point in time. So we make a simplifying assumption. Namely, we assume that the space use or the long run density or the utilization distribution within months is stationary. So basically, we assume that lambda is fixed across time intervals, and this means that we only need to estimate cumulative effort from our observers. This is a much easier task. Why? Because this E hat integrated over S and T is going to be a much smoother process. So moving on from that, we still have a problem. We need to estimate, or estimating the cumulative effort from citizen scientists remains tricky. So this is why we turn to the whale watching industry. Why? Because the whale watch industry provides sightings in this massive citizen science database. The whale watching industry is a huge operation in this area, taking over 500,000 people annually from over 20 ports. Interestingly, fears around the safety of the southern residents led to the creation of the Soundwatch boater education program. Now, amongst other things, Soundwatch keep really detailed data sets and release annual reports on the trends of the whale watching industry, including the number of vessels per year, month, even time of day that are out on the water. We have knowledge of the number of boats leaving per port, where they go, and this allows us to build detailed estimates of where the boats go per month for each port. However, we do not have knowledge on which whale watch vessel reported each sighting, only that it came from one of the vessels. This forces us to make the assumption that observer efficiency is the same across all the whale watch vessels. Furthermore, we have no spatial overlap between the presence only and the presence absence data sets. And so we have to assume the observer efficiency again is the same across the DFO funded boat and the whale watch boats. This is probably our most questionable assumption. But under this assumption, and the details are left for the paper, For any region S and time window T, we just need to estimate the total number of boat hours that fall in S and T. So this is a reasonably easy task to do. We do this, using the reports from SoundWatch, we put these informative Bayesian priors on all of the components used to estimate where the whale watch boats go and how many boat hours go into each of our computational pixels. And so we develop a stochastic search effort emulator. And this is one example realization of our total search effort from all observer types. We do this 1,000 times. We fit the model 1,000 times in INLA. And we get, as a spatial statistician, we get posterior means and posterior standard deviations of each of the pod's density or species for each month. This is shown on the log scale. But my concern then was, do I really expect policymakers to be able to identify hotspots from these kind of plots? I argued no. I turned towards exceedance plots. Under our Bayesian framework, we can compute the posterior probability, pointwise probability, that the whale density is above any threshold we choose. So I choose a high threshold, and I compute the probability that it is in that the true density is above that threshold. And I then remove all pixels that have posterior probabilities below 0.95. And this really helps us to identify regions of high southern resident killer whale species. Now, you might be wondering, can I use these ideas and this framework for your own applications? Absolutely. Good news, we're writing a paper, it's almost out. It's a general framework, it's a marked log-Gaussian Cox process framework. We will really sort of explain what those assumptions are using a causal DAG. These are very easy to put your assumptions out to people to scrutinize. And lastly, we do a thorough simulation study that really shows this method works. And on the right-hand side, in cases where it doesn't work. I can answer any questions on this. I just wanted to leave you with a little comic about a really obvious example of a false negative sighting. Thank you so much to the organizers. Really appreciate everything you've done to making this such a fantastic conference.